I welcome you for this presentation. In this presentation, we are going to discuss about public key crypto systems through, that is elliptic curve cryptography. In the last presentation, we have discussed about two public key crypto systems. One is Diffie-Hellman key exchange crypto system and another one is LGML public key crypto system. This is the overview of this presentation, that is introduction to this elliptic curve cryptography, then real elliptic curves, then finite elliptic curves, then elliptic curve cryptography, then ECC with Diffie-Hellman, then ECC encryption as well as decryption, then ECC security applications of elliptic curve cryptography, followed by summary of this presentation. So we know the main important or most important public key cryptography, that is RSA, that is Shriver-Shamir-Edelman and Diffie-Hellman. These two crypto systems use either the integer or polynomial arithmetic with large numbers or polynomials. We have already discussed these crypto systems, and these crypto systems use very large prime numbers and polynomials. So what happened with these crypto systems means they imposes a significant load in storing and processing keys and messages. So the inventors of this elliptic curve cryptography, they proposed an alternative to these crypto systems. That is, they used, instead of the integers and polynomial arithmetic, they used elliptic curves to define any crypto system. So that is the elliptic curve crypto system. This elliptic curves means they are not ellipses, they use some cubic equations. So only the name elliptic curves, and in the elliptic curve cryptography, these elliptic curves are used. And this elliptic curve cryptography offers the same security with smaller bit sizes, and this crypto system is newer but not as well analyzed compared to other crypto systems. But this crypto systems, this elliptic curve cryptography is also used in various applications wherever we need a smaller storage. In such cases, in some smart applications and all, this elliptic curve cryptography is used nowadays also. So before going into this elliptic curve cryptography, we need to know what is a real elliptic curve. Here you can see the pictorial representation of the elliptic curve. Here this equation, that is y square equal to x cube plus x plus 1 is plotted. That is, here we are having 2 points P and Q, and the meeting point of this P, see here we are having the minus P plus Q and P plus Q. The meeting point, we are calling it as R. That is, it is a real elliptic curve is an elliptic curve which is defined by an equation in two variables, that is x and y, with the coefficients. Here we are having the variables, that is y square equal to x cube plus ax plus b. So here we are having y as well as x, and here it is represented as a cubic elliptic curve. Consider a cubic elliptic curve, that is y square equal to x cube plus ax plus b. Here these values, that is x, y and a and b, are real numbers, and we are defining a 0 point. That 0 point we are calling it as O. Suppose we are considering a point, that is E of a comma b, that will satisfy this elliptic curve cryptographic function, then we have an additional operation for this elliptic curve, that is geometrically sum of P plus Q is the reflection of the intersection of R. See here the reflection. What do you mean by reflection here? Here we are having P plus Q. This side, reverse side, we are having minus P plus Q. So the meeting point, the intersecting point is have the reflection of this P plus Q. Here we are having the some P plus Q. The reflection is here, that is minus P plus Q. Here this is the meeting point. The dotted line represents the meeting point, and this is the meeting point we are having. The meeting point, it is represented as a minus, the reflection of the given R value. That is called as real elliptic curve. The structure, the pictorial representation depicts it is a elliptic curve. This is the representation for elliptic curve. Next is finite elliptic curves. Here This elliptic curve cryptography uses curves whose variables and coefficients are finite. We all know that the Galois field, that finite field, Galois field of 2 power n we know, and Galois field of p also we know. So here in this elliptic curve cryptography, we are having two families of this elliptic curves. One is the prime curve and another one is the binary curve. And this prime curve is mainly used in software and the binary curve is used in hardware. So here you see the prime curves EP of A comma B is defined over ZP. You know what is ZP? It uses the integers modulo a prime number, that is set of prime numbers. Suppose we are having P as 7, then we can give the numbers as 0 to 6. Likewise, we are having the set of prime, that is integers modulo a prime number. So they mainly this prime curves are used in software. Then binary curves, that is E2M of A comma B is defined over Galois field of 2 power n. And this uses the polynomials with binary coefficients, and mainly this binary curves are suited for use in hardware applications. So here in this elliptic curve cryptography, we are performing some addition. So how we are performing addition means it is analogous of the modulo multiplication. How we are performing modulo multiplication, the same way only here we are performing the addition. And ECC perform repeated addition, which is analogous to modulo exponentiation. We all know the multiplication we can mention with respect to addition. If it is m square, then we can represent this m square with respect to the addition also. So any multiplication we can represent with respect to addition also. So here the repeated addition, that is exponential part, that exponentiation part is also represented using this addition. And but it is hard, it is a hard problem. How hard it is means it is equivalent to the discrete logarithm calculation in Diffie-Hellman. In the Diffie-Hellman, we have the discrete logarithm calculation, and in the Diffie-Hellman, we have seen that discrete logarithm calculation is difficult. That difficulty, that is the hard problem, the difficulty is similar to that of factoring problem in RSA algorithm. So similarly, here we have to, if you want to perform these operations, this is a hard problem and which is similar to, equivalent to the discrete logarithm calculation in Diffie-Hellman. Suppose you see Q equal to Kp, where Qp belong to a prime curve. Prime curve, it is mainly used for software, and Q equal to Kp, it is it belongs to the prime curve, and when it becomes easy means if you know, if you want to compute Q by knowing K and P. If you know K and P, then it is easy to compute the Q value. But it is hard to find K value if you know only P and Q. So it is very difficult if you know, if you want to find the K value, because this K value is kept secret. So it is very difficult to find out the K value. But if both Q and P are known means also it is very difficult. This problem only we are calling it as the elliptic curve logarithm problem. So here we are telling that in elliptic curve cryptography also we are having one problem. That problem is similar to that of the discrete logarithm problem in this one Diffie-Hellman public key crypto system. Here this problem, that is Q equal to K comma P, if you want to compute K value by knowing only Q and P value, it is very difficult and practically infeasible. That problem only we are calling it as elliptic curve logarithm problem. Next is elliptic curve, which is cryptography, that is similar to that of Diffie-Hellman. How it is similar and what are the dissimilarities between this Diffie-Hellman and ECC? Let us see. Here also we can do key exchange analogous to the Diffie-Hellman. We know the Diffie-Hellman is for key exchange, and there what we did means that is Alice and Bob just selected a Q value and alpha value. Q means it is a prime number, Q is a prime number and alpha is a primitive root of Q. Likewise, Alice and Bob chooses this value. Then Alice separately computed the private key. Then Bob also computed his private key. Then using the private key as well as this Q and alpha, they generated a public key. And then they shared the public key to the other party. That is, Alice generated a public key and shared it to Bob, and Bob generated a public key and shared it to Alice. Similarly, here also, there we had a value. Here we are having a curve. That is the only difference. So only here we are calling it as elliptic curve cryptography. Instead of that variable or values, here we are having a curve. With respect to the curve only, both the parties have to compute the private key as well as public key. Then they have to share the key. Finally, using that public key, they are generating a key, and the value of that generated key is same. In the earlier case also, in Diffie-Hellman, we have seen one example, and we have generated, both the party generated a key that is equal to 160. So both generated the same key finally after sharing the public key. That public key is made up of whatever the private key they generated, and finally they generated a key. That key value is same. Both Alice and Bob generated the same key. That is the key exchange problem. Here also it is similar to that only. So here users select a suitable curve, that is EQ or EQ A comma B. That is on a curve, that is elliptic curve of A comma B. Then they are selecting a base point, that is G equal to x1 comma y1. Here some point also we have to compute, and the point y, two values are there. In x-axis, what is the value? Suppose we are having a value here, what is x value and y value? Likewise, they have to select a point also, and that point must be large order n, such that ng equal to O. What is O? It is a 0 point. And A and B select private keys NA less than N and NB less than N. Then they are computing the public keys, that is PA equal to NA into G. What is G? Here we are having a G value, that is a point G, x1, y1, G, and PB equal to NB into G. Then they are sharing the shared key, computing the shared key, that is K equal to NA PB. Then here this side K equal to NB PA. Using the public key of other party, they are generating the key. So finally they are getting the same value for the key, that is K equal to NA NB into G. Attacker would need to find hard. It is very difficult. So in this elliptic curve cryptography, the attacker has to find K, but it is a very hard problem, because we know Q equal to KB. We are having KP. So if you know P value as well as Q value, and if you want to compute K value, it is very difficult. It is a hard problem in elliptic curve cryptography. So let us see one example how the shared key is generated. Here P equal to 211. Then for EP of 0 comma 4, the point given is EP of 0 comma minus 4. Then they are choosing G equal to 2 comma 2. Now how they are computing the value? 241 G equal to O. It's a 0 point. Then into NA equal to 121. The value is 121, and PA equal to 121 into, how to compute PA equal to 121 into that G value. 121 is ONA into G value. So we are getting the value as 115 comma 48. This is a modulo multiplication. So 115 comma 48. Then NB value equal to 203. So we are computing the PB values, that is 203 into 2 comma 2. That is 130 comma 203. Just modulo multiplication we have to perform. So finally we are having the shared secret key, that is 121 into 130 comma 203 equal to 203 into 115, because both the parties are computing a different value, that is NA into Q value they are computing, and PB also computing NB into Q value. Then we are getting two different values, that is 121 into 130 comma 203, and another party is computed 203 into 115 comma 48. So finally both the values are 161. Both the values, what values we are getting is, from these two we are getting the values as 161 comma 169. That is, for choosing a single number as the secret key, we could simply use the x coordinates or some symbol function of the x coordinate. So here the values, we are using a point, and with respect to the point only, here we are performing the computation. So here mainly we are not working on any variables. Here we are working on some points, that is x value and y value, because in the elliptic curve we have to plot a point. So by plotting the point, then only we can use that point with the public key crypto system, that is in the elliptic curve crypto system. So next is the encryption, the ECC encryption decryption process. That is, here we can have several alternatives, but here we are considering only the simplest encryption decryption algorithm. That is, here we are first encoding the message M as a point on the elliptic curve PM. Then we are selecting a curve. Here instead of that Q value and the alpha, that is the primitive root of Q, here we have to select a suitable curve and a point G in this, as in the Diffie-Hellman. This is similar to suitable curve, that is similar to Q, and a point G that is suitable to alpha, which is the primitive root of Q. Here each user chooses a private key, that is NA, that must be less than N, and computes the public key PA equal to NA into G. Then the encryption process is performed, that is CM equal to KG comma PM plus K into PB. Here K is a random, selected random. Decryption, how we are performing the decryption operation is PM plus K into PB minus NB into KG. Then we are substituting that, that is PM plus K into, instead of PB, what is the PB value? It is NB into G. So we are substituting that value minus NB into KG. So finally what we are getting, this K NBG minus NBKG, both are cancel out, that is positive as well as negative value, and finally we are getting the plain text, that is PM we are getting here. Here we are getting the plain text. So the encryption and decryption process in the elliptic curve for cryptography works on this principle. It is similar to that of Diffie-Hellman. The only difference is, instead of Q value and the alpha primitive root of Q, we have to select a suitable curve and point G, and we have to perform the encryption as well as decryption process. Let us see one small example how this encryption and decryption is performed. That is, here we are having a p value as 751 and the point is -1, 188, and we are having the g value as 0, 376. Then we are assuming the plain text as 562, 201. 562, 201 is to be sent, and that the sender chooses a random number k equal to 386. Then we have to directly substitute all these values in the formula, and we are getting, assuming that the receiver's public key PB is 201, 5. Then we are having whatever the formula we have seen earlier. If we have to substitute those values, and finally we are getting the ciphertext. Consequently, this value is sent as ciphertext. These two values, that is 676, 558, 385, 328 is sent as the ciphertext. So if you want to perform decryption process with the help of the ciphertext, you have to apply the decryption equation, then you will be getting the plain text. Whatever plain text PM equal to 562, 201 will be getting as plain text. So coming to the elliptic curve cryptography security, this algorithm relies on elliptic curve logarithm problem. So here one disadvantage or hard problem in this elliptic curve cryptography is elliptic curve logarithm problem. So here this is this can be how we can perform this operation in a fast method, means we have to use one fastest method, that is polar rod row method. What is polar rod row method? Means it is algorithm for integer factorization, because here we are having the elliptic curve logarithm problem. So here we are using the polar rod row method. So this polar rod row method is mainly for integer factorization. That is why we are using this polar rod row method, means this method uses only small amount of space, and mainly elliptic curve cryptography is for in order to reduce the storage space only, we are going in for this elliptic curve cryptography. So here for smart applications, because the storage capacity is very small in these smart applications or smart devices, small devices. So in such cases we can use this method, and it is expected running time is proportional to the square root of the size of the smallest prime factor of the composite number being factorized. So what is polarized row method is given here. So compared to the factoring problem in RSA, here we can use much smaller key sizes, and it is equivalent, we are using the equivalent key length computation, which are also roughly equivalent to that of whatever the factoring problem we had in RSA, and hence for similar security ECC offers a significant advantage, computational advantages. So comparing to this RSA and Diffie-Hellman, in order to have a smaller key size, or in order to have a small amount of space, occupy small amount of space, this ECC is providing some significant computational advantages compared to other methods. So these are the comparable key sizes for equivalent security. Here we are comparing the scheme symmetric with the ECC with the symmetric scheme, then RSA and digital signature algorithm. So here for the symmetric scheme, if the key size is 56 bits, then for ECC it is 112 bits, and then for RSA and DSA it is 512 bits. Likewise, the key sizes are varying with respect to the particular scheme, that is whether it is a symmetric scheme or ECC based scheme or RSA or DSA scheme, but the security provided by this ECC is also significant compared to the symmetric scheme as well as RSA and digital signature algorithm. So these are some of the applications of elliptic cryptography. That is, nowadays we are having many devices. All those devices are very small and have limited storage and computational power. So where we are applying this elliptic cryptography means in wireless communication devices, many smart cards, then web servers that need to handle many encryption sessions. In such cases, we are using this elliptic cryptography. And any application where security is needed but lacks the power, storage and computational power that is necessary for our current crypto systems. Nowadays, as the technology advances, more and more small devices are available, and these small devices need small storage capacity with proper security. So in order to ensure proper security for these smart cards and smart devices, wireless communication devices and web servers that need encryption between sessions, we are going in for this ECC. So let us see one example problem with respect to the working of this elliptic curves. Here we are having the points P of x1 comma y1, and 2 points we are having P1 as well as Q, and with the P not equal to minus Q and P plus Q equal to x3 comma y3 is determined by the following rules. So here it is given x3 and y3 are given, or all mod operations. Always keep this in mind, all mod operations. And where lambda, here lambda is there, lambda square, lambda is there. So lambda, how we are defining? Y2 minus y1 divided by x2 minus x1 if p not equal to 0. And if p equal to 0, then we are defining the lambda as 3x1 square plus a divided by 2y1. Then we are defining the p value, p equal to 3 comma 10 and q equal to 9 comma 7. Then you have to compute the lambda value, just apply here, because this one we can take it as x1 y1. What is this one x1 y1, p equal to, we are having x1 and y1, this is x2 and y2. Then you have to apply these values with respect to this lambda formula, then we are getting the value. Then we are finding, using the lambda value, we are applying that lambda value to x3 and y3, and we are getting the value of x3 and y3, that is 17 mod 23 and 20 mod 23. Then we can compute, because p plus q equal to x3 comma y3. So p plus q equal to, you have to compute whatever the value we have used, that is we are x3 is 17 and 20 is y3. This way we are getting the value. Then suppose if we want to find 2p, then how we are doing? Again we have to perform this for 2p. Here we know what is a p value. So in order to provide 2p, we have to substitute the formula, and we are getting a value. Again, multiplication is defined as repetitive addition. Here are 2p. 4p means how we have to do, 2p means we have to do p plus p. Suppose 4p we are having means we have to do operations like p plus p plus p plus p. Likewise, we have to perform repeated addition. In order to perform multiplication, we need to provide repeated addition. That is the main concept in the elliptic curve cryptography. So in this presentation, we have discussed about introduction to elliptic curve cryptography, then different types of curves, that is real elliptic curves and finite elliptic curves. And finite elliptic curves, we have seen two curves. One curve is used for this one software, and another curve is used for the hardware. And we discussed about the functionality or working principles of elliptic curve cryptography. Then how this is analogous to Diffie-Hellman, that also we have discussed. Then how the encryption as well as decryption process is performed in this elliptic curve cryptography. Then coming to the security, how this elliptic curve is secured compared to other public key crypto systems. That is, it is providing significant security compared to other public key crypto systems, and where we are using this elliptic curve cryptography. That is the applications of elliptic curve cryptography. So we have discussed some public key crypto systems, that is under public key cryptography. We have discussed RSA algorithm, then Diffie-Hellman key exchange algorithm, then LGML public key crypto system, and elliptic curve cryptography, that is elliptic curve crypto system. Thank you.